So here I will talk to you about designing schema for Innodb. So if Innodb is probably the most extensively used storage engine for MySQL, I know there's many other talks covering about the same topic. All consultant has their own view on that. So pick the best from everybody. It's all often based on the type of success we have used fixing problems. So about myself, I've been with Percona since 2009 as a principal architect. Previously, I was with Sun and MySQL. I left when Oracle acquired Sun. My focus is mainly on MySQL HA distributed system. That include NDB cluster, pacemaker, and now I'm looking a lot at Ceph. I have a database and mostly science background, so I studied in physics at the university. The plan here, I'll first describe what makes Innodb different from other storage engine, what's special. Basically, I will tell you how to cheat it. So if you know how it works, you can better use it. And then we will design, let's say, a new uber fantastic file sharing application, a bit like Dropbox Box or Google Drive. And of course, I'll do all the mistakes while doing the schema so that we can then fix it. So, Innodb internals. The first most important thing in Innodb is the Innodb buffer pool. It's where Innodb does its work. It never works on file directly. It loads pages into the buffer pool, do operations, and it's written down after. So there's helper, threads, and function around that to make that as asynchronous as possible, the file operation. So an unallocated page here is indicated in yellow. So there's another thing, the system table space. If you're not using Innodb file per table, everything is there. But in general, you have some allocated page. And one of the most important part here is the dictionary, where Innodb knows about its table space, its tables, columns, everything is there. You have the change buffer. There's been a few talks about change buffering. It's basically, Innodb is a super cheater. When you insert a row, it has secondary keys. The secondary keys pages are not in memory. Instead of waiting, loading to disk, and updating, it just set that aside. I'll do that later. It's a huge, huge performance gain. You cannot imagine how large it is. Undo, so that's basically for transactions. So people must be able to see rows as how they were when the transaction started. It's Innodb is MVCC, so it keeps a consistent view, and that's kept there. Now, it's too far. You have table files. So for a given table, if you're running with file per table, of course, which I suggest you do, each table has its own file with pages in it. And there's one other thing, the Innodb log files. I used a circle here because it's a ring buffer. It can go very well doing writes, recording writes, but if the head catch the tail, it has to stop. And that's all the thing about flushing in MySQL is to prevent that. Because when it catch the tail, it stop doing queries until it's able to proceed. So let's just run a short life cycle of a simple update query. A few things are not exactly right, but and what I will show you, but the general principle is there just to help see what's going on. So basically the query is started, the optimizer realized I need 2 pages, so it loads the pages in memory. Then the query run, it update a page and save the undo. Actually, this is not done there. The page is already in the buffer pool and marked dirty there, but it's easier to see that way. The commit is not returned yet. When it will return, only when the log files has been written. So later, the page is written, make clean, and the entry in the ring buffer is cleared. And eventually, the purge will remove the undo operation. So that's just general processing inside Innodb. So in general, you want the buffer pool to be large as you can, to hold most of your data because it saves I/O for reads. The log files, you want them to be big enough so that you're not always writing each change. So, and a page can have a change to have more than one write. So let's see. So Innodb stores the rows inside a B tree. It's the B tree of the primary key. The secondary keys are also B trees, but the value that they store is not the row, it's the value of the primary key. So if you have a very large primary key, it makes the secondary keys bigger because it's saved for each entry. But how come some people have no primary keys and it works? Because if you don't define a primary key or a unique key on a not nullable column or columns, Innodb use a hidden one. So it's really not great, so try to avoid that as much as possible. But it's inserting a primary key for you, even though you cannot use it directly. So let's look at a B tree, the way it looks. It starts by a root node. The root node is really the handle that MySQL has on the table. When you access a table, it starts by the root node, and then it processes the memory structure. So here, it's an integer. Normally, there's many more entries. Here, I just have 3, which is fine. But since Innodb has 16K pages, it's very common to have many hundreds leaves. So at each level, if it's smaller than, bigger or equal to 1 and smaller than 12, it goes to the first node. Between 12 and 22 here, and over 22 will go here. That's the way it's navigated. So that's the root. You have nodes, which doesn't have data. They just point to other pages. And eventually, you hit the bottom where you have leaves. The leaves are where the rows are stored. I mean, the root could be a leaf if you have a table with 1 row. But eventually, you have, as your table grows, you have a few levels there. It's very rare to have more than 3 or 4 levels. You need a big table because the fan out is large. So here you have the primary key value and the row, which is all the other columns. So a secondary key is about the same thing. Let's say here on gender, you go down, you have the nodes, so all female are here, all male are on the other side. And at the last level, you have all the entries with the primary key values of the rows. So when you do a search on a secondary key, you dive the index here, you find, let's say, 26, you go back here and dive for 36 and find it there. So that's the way it works. So let's see. So that's all I want to tell you about the internal, but it's important to understand the remaining points. So let's see. I want to develop my Uber fantastic file sharing application. So say, oh, I'll have users. Users have name, passwords, and some other attributes. I want to have preferences so that they can change a theme, the ordering, whatever they want. I will define a set of preferences here. They will have objects that they save, so a file, folder. Those objects can be shared between users. So I have a table to refer to the share. So it's a many-to-many table between object ID and user ID. And of course, I want to log all the activity. Sorry for the drawings, the lines. That's OpenOffice limitations. So all the activity will be logged. I want my marketing guy to be able to sort patterns and things like that. So that's my basic schema. Probably have more tables than that, but it's the functionality I want are all in there. So I learned at school that UUID are very useful. There's never collide, it's unique, it's huge key space. So I decided to use UUID as a primary key. So, but never copy that. It's the worst schema you can imagine, so don't do that. So use char36 for UUID. That's perfectly fine. So I define all my things. I want to use char because I know it will always be 36. And my password are hashes, MD5 hashes. So I know that's char32. Everything else, I put a varchar. My framework, add, updated add, created add. That's perfectly fine. I want a last login, gender. That's all good. And I will create keys. So primary key, of course, would be user ID, ID name, password, and I want to have support foreign characters, so I'll be using UTF-8. So user prefs, about the same thing. I have another UUID column for the primary key. I have the user ID, and I have a key on user ID. So it's fairly nice there. Objects, about the same pattern. So UUID for the primary key. Parent is the object where it belongs. If it's 0 by default or a series of 0, it's the root of your folder. If it's not, then it's a folder under it. Owner is the user ID that owns the object. So I have a type and name, URL store, because I want to use something like SwiftStack, OpenCef or S3 to store the file, so I won't have to bother with storage. Version deleted, so same type of pattern. I created the keys I think are needed. So, and of course share. That's another one. So share object, and so here I have share object and user ID, the keys I needed, I think. And the last one is activity log. So same thing again. So I'm logging all the operations. So I have a time. I have the IP from where it's coming, return code, the action. So that's fairly simple. So I start coding. Went well. I have a good team of developers, and they're all very inspired. We did some pilot testing on our laptop. It works. Superb. Then before making it available, we tried to scale a bit more. Oh, didn't go that well. At a few 100,000 users, performance was not that great. What happened? Data set is much bigger than we thought it would be. Database is using much more CPU than we thought. Should not be that much. And as soon as we're out of the buffer pool, that's super slow. What the hell is coming? And the disks are very busy as soon as we are out of the buffer pool. If we are to have millions of users, it will not be great. So what can we do? Easy. I see servers with 1 terabyte of RAM. It's a bit expensive, but would fit for some amount of time. I could also use PCIe SSD cards to be very fast, so my IOPS are not a problem. Could start sharding, but in staging, it's a bit problematic. Would mean I would need to shard a lot. but maybe the schema is not that great. So the guy asked an external consultant, let's say Percona, to review the schema. So what happened? So first thing, the guy reviewed the types. The consultant looked through the types and tried to make things better. So because if you use a type that is well optimized for what you are doing, it takes less space in memory, so you cache more. Common sense. So if you have more in memory, you don't need to access disk as often. Less read and write to disk. And also, if the types have a higher cardinality per bytes, the comparison are faster. First problem, I've defined a lot of char with UTF-8. What that mean? Char has to reserve 3 bytes per UTF-8 characters. That's a common error that people do. So when you define a UUID columns with char 36, what you end up doing is a char 108. It's not visible, but MySQL will pad up to 108. It has to, because it cannot assume that you will not be using for all the characters 3 bytes. So that's first there's a problem. And I had many keys on tables where the primary key is a UUID and the secondary key is on a UUID column. That means every entry is 216. That's huge for a secondary key. So right there's a problem. So the solution at first, if we are to keep those, is to use varchar. Even though there's a length in it, when there's no 3 bytes character, it will use just the required space. So even though a UUID never has 3 bytes, with varchar it will use 37 instead of 36. Or best, for those columns that you know that will never have 3 bytes, you define them as latent 1. So another thing, I've defined a few varchar 255. Why? Why do people stop at 255? Do you know? It's common. People will all do varchar 255. 1 byte length. But remember, it's UTF-8. So this is 700 something in length. So the real stop is at 85 when you're using UTF-8. So the same logic would tell you to use varchar 85, because 85 times 3 is 255. So, so as soon as you go over 85, it's no longer 1 byte for length, it's 2. So, in such a case, if you just want to max the 1 byte length, use 85, or define to a proper length that your application will limit. Low cardinality columns. Let's say you have object of type, which is defined as a varchar. It can have only file, folder, or link. It's the only authorized values. Why would I store a varchar when I know the key space and it's so small? So, and same for user pref names. I only have a few. It's really, you can list them. So in such a case, you should use enum, it's a solution, or even better, a dictionary table. So you have to join, but it's a very small table, and you define, let's say you have a table object type, where you list all the values, and you store in the object table only, let's say, a tiny int that will point to the value. So you save a lot of space, and you remove all those varchar on redundant data. That you, instead of having the word file written to all the rows, you have only 1 byte, which is a tiny int value pointing to file in the object type table. Is that clear for everybody? Datetime. It's a convenient format. It stores an arbitrary date and time. But with 5.5, it's 8 bytes. With 5.6 plus, it's 5 bytes plus the precision you want it to have. 5 bytes, I think it's second. If you want microsecond or something, it grows. So it's still a fairly large type. If you're only interested in things like created that, updated that, and which is obviously close to now, and you don't mind having microsecond, you can use timestamp. Timestamp is 4 bytes. So it's smaller, especially with 5.5. So there's a saving there. It's a small type, easy to compare. It's very good. Next, int types. So in our example, we had deleted was an int, 4 bytes. But it's really a flag. It's 0 or 1. So in such a case, a tiny int would do it. It's possible to set bits. I'm not covering it here, but you can set a bit too, a bit type. If you don't use any negative values, take the liberty to put on sign, especially on keys that are auto-increment and for primary keys. It doubles your key space. So if you happen to be very successful and you have a lot of people, you won't have to alter your tables in production to change the int type to a bigger type. Okay, another big point here. Big int is really, really big. If you really need it, maybe Facebook has enough users to go over 4 billion, and they do some strange thing with their primary keys, it's fine. But if you don't plan to have more than 4 billion rows in a table for the primary key, or the value of the integer column will never grow more than a few hundred million, don't use big int. It's 8 bytes. It's enough to enumerate all the ants on Earth. There are many, 1 billion times. So it's really, really large number. If you're storing, for example, IPs, in my activity log table, I was storing the IPs from where the call was coming. A very neat way of storing them, very tight, is using an integer unsigned with the inet A to N and N to A functions. It basically converts the 4 bytes of the IP address to an integer, 4 bytes. It's the packing is great, and it's easier to search, to store, so it's a very good thing. Blob text fields. If basically the rule, the way it works at Innodb, if there's a few exceptions, but in general, if the blob column is bigger than half a page, it stores in, the remaining is stored in an overlay page, and only a prefix is kept. So that means when you retrieve a row with a blob or text fields, you have to retrieve the row and then go somewhere else to retrieve the remaining part for the blob, especially if you do select star. Even though you don't need a column, that's fairly expensive. There are also, when you do a temporary table, the memory engine doesn't support blob or text. So it has to go to on-disk temporary table, which is, has a higher cost. So one thing you could do, you use a var binary or maybe still a blob, but you compress in it. You may be, it will be much easier to fit within the same row your data if you decompress it. If it's slightly bigger than half a page, it will fit after the compression. MySQL has compressed and uncompressed functions for that. So you ready? Good thing. it's a large varchar. It's very slow to compare. You have to understand that when Innodb compares a varchar, it has to go through collation, through char set and all that, and it's doing it byte per byte. So it's a loop that goes over 36. So it's slow. When you compare an integer, there's no collation, no char set, and it's 4 bytes at a time done by the processor directly. So it's very quick. So large varchar, you index if you really need to, but be careful with these. Also, hex per byte has 16 of cardinality. So you need to go far into to really see a difference. While with an integer per byte has 256, which is very great. It inflates, like I mentioned, the size of the secondary keys. So so your data on disk is bigger, you store less in your buffer pool. And most important, it causes random inserts. This is especially problematic for the activity log table because you will be inserting all your clicks nearly on your side there. And if for each of the clicks you are going in randomly in your table, remember that the leaves are very numerous. They are at the bottom of the tree. So if something will not fit in memory and will be sent to disk, it is those leaves. But you're randomly inserting. There's no hot spot in it. So every time you will insert, you may end up needing to read the page, write it, and it will never receive another write because there's so many leaves. It will have to be written back. So it's 2 IOPS per write. That's very bad. So in such a case, when you need to insert a lot, an integer on sign auto increment is a much better solution because do I have the B2? Yes. So great. So if you do that, all the new rows will be at higher value of the primary key. So you just have inserted 35, 36, you'll be inserted 37. They all go to the same pages. So you don't need to read. It's already there. And you fill one, write to disk, and you are processing the next one. So inserting in primary key order is uber important here because it saves you so much. On my laptop, if I insert in random order, I do less than 100 rows a second when it's no longer in the buffer pool. If I do in primary key order, I can go at 20,000 easily. There's no problem there. So it's a big gain. Okay.
Question.
Yes?
Is there any disadvantage in using unsigned versus signed in MySQL?
No.
Not at all?
Not at all. Except that you cannot put a negative value. It's probably obvious. Yeah. User pref, objects share. Okay, so those are all tables that are as a child relationship with user. So when a user logs in and wants to retrieve the prefs, it will have to go to the user pref table and retrieve all the preference based on the secondary key value. Same for object and share. So let's say we did the search on the secondary key for user ID equal 3. It returned 8, 12, and 27. So on the leaf level, that means 8 is here, 12, and 27. So if my server is out of cache, so the buffer pool is, let's say, 32 gig, but I have 1 terabyte of data. So very little of my data is in the buffer pool. So I'll have to read the 3 pages. So it's approximately 1 IOP per row retrieve, which is super bad. I mean, here is let's say it's the preference, but if it's the objects, a user might have thousands of files saved. It's perfectly valid, and you want that. It means that they are using your service. So this is a bad situation. So what can we do? Let's say we reorganize the primary key. So first, Object ID, which is our primary key. Likely now it's an integer based on what we have discussed. An integer auto increment maybe. So now we moved it as a unique key. So the auto increment still work, unicity still work, the application, if it needs to access by object ID, it works perfectly fine. But we reorder the primary key. So now we will use user ID and object ID. That caused the rows to be reorganized on disk. The reorganization is like that. So user 1, user 2, user 3, oh, look there. Under it, 8, 12, and 27. What happened? They are all on the same page now. At worst, a few pages, like 8 here as 3, but they are consecutive pages. And Innodb is cheating. You don't need to walk down the B tree each time. There's a shortcut between the pages. So that's fairly cheap. That's super cheap. So now, it's no longer one eye up per row. It's one eye up per, or one or a few eye up per request. It's very different. And since the Innodb pages are large, it's very rare that you have these, except if you have large rows. That's a very, very big gain